Welcome. In this session, we'll look at initial value problems. Recall that general antiderivative is not unique. It really stands for a collection of functions. If I know just the derivative, I cannot pinpoint the original function. If I had some additional piece of information, I might be able to pinpoint it by determining the specific value of the constant of integration. The simplest case of this is what is called the initial value problem, where we know the value of the original function at one specific number. The name comes from physics. Suppose I'm traveling on a straight road. If I know my speed at every moment, I cannot quite figure out where I am. But if I know where I started from, then I can. So if I know my initial position and speed at every moment, I can get by what's called dead reckoning my position function. The initial value problem is the same thing done using calculus. It's still called initial value even if the value of the function at some number is given, not necessarily at 0. Let's look at a simple example of how we do this. Here I have f prime of x given as 6x squared minus 8x plus 9, and the value of the function f is given, f of 1 is 2. First I find the general antiderivative of 6x squared minus 8x plus 9. It's just the power rule applied term by term. I get 6x cubed over 3. 6 over 3 is 2, so 2x cubed. Minus 8x squared over 2. Minus 8 over 2 is minus 4, so I get minus 4x squared plus 9x plus the constant of integration. Now f of 1 equals 2, which means that if I plug in 1 for x, the function should come out to be 2. So you plug in 1, you get something that involves the constant of integration, c. You set that equal to 2. That gives you an equation involving c, and you solve for c. Of course, these equations in these types of problems will be very simple because you get some number plus c equals another number. If I simplify the left-hand side, 2 minus 4 plus 9 is 7. So the equation is 7 plus c equals 2. So c is 2 minus 7 or negative 5, which means the original function is 2x cubed minus 4x squared plus 9x minus 5. Remember, in these problems you are asked for the original function, not for c. So your answer is not the value of c, but the value of the original function, which is the general antiderivative with the value found for c replacing the plus c. Let's look at one more example. This time we are solving the initial value problem. Dx over dt equals the quantity square root of t cubed minus t over the quantity square root of t cubed. X is 4 when t is 9. That's what x of 9 equals 4 means. Because since I don't have a quotient rule, I have to rewrite the derivative. I'm going to distribute the denominator. I'm also going to write square root of t cubed using fractional exponent. So I get 2 to the power 3 over 2 minus t over t to the power 3 over 2. If I distribute the denominator, I get 2 to the power 3 over 2 over t to the power 3 over 2, which is 1. Or you can use the rules of exponent and get t power 0. And the second term will be minus t to the power 1 over t power 3 over 2. So that's minus t to the power 1 minus 3 over 2. 1 minus 3 over 2 is negative 1 half. So the derivative dx over dt is 1 minus t to the power negative 1 half. Its general antiderivative would be, for the first term, just t. For the second term, I add 1 to the exponent, divide by the new exponent. Negative 1 half plus 1 is positive 1 half. So I get t minus t to the 1 half over 1 half. And then I have the constant of integration c. Now I'm going to simplify this a little bit. Negative 1 half plus 1 is 1 half. So the second term is minus t to the 1 half over 1 half. 1 over 1 half is 2. So the second term is minus 2t to the power 1 half. Now I'm going to use the given value to determine c. When t is 9, x is 4, So you plug in 9 for t, the function should come out to be 4. So 9 minus 2 times 9 to the 1/2 plus c is 4. 9 to the 1/2 is 3. 9 minus 2 times 3 is 3. So 3 plus c equals 4. So c is 1. And I put this back in the expression for the general antiderivative. That gives me the function. I also went back to radicals. T to the 1/2 is square root of t. So x is t minus 2 radical t plus 1. This concludes our basic examples of initial value problems.